Hey, Megan. How's it going?
Sorry. Hi, Sam. How are you doing? Yeah, I'm good, thanks.
Good, good. Great to see you.
And you, how's the new job?
It's good. I mean, it still feels new, but I guess I've been here for like a year now. So at some point, I got to stop calling it new again.
And what are you working on?
I'm also have delved into the experimental world. So yeah, I'm doing melting experiments with sulfides, kind of pursuing some of the ideas that I talked about in the dissertation, looking at
Nice.
how oxidized bodies might have this sulfide core formation and how that works physically and what it looks like geochemically, so that we can maybe look for trace element evidence of that, like among some of the iron meteorites.
Oh, wow. Okay.
Yeah. So we're making good progress on it. But now we're working on the geochemical side of things. For a while, we were looking at like physical mechanisms and seeing how that can work by maybe percolating these melts through mostly solid mediums, basically just by capillary action between grains, which turned out to be a bit more technically challenging than we initially imagined. And so now we're using natural samples to do it rather than the entirely synthesized materials we were doing before. It's just, the meteorites solve those problems themselves. It's things like textural equilibrium and that kind of stuff that's pretty hard to attain in, a 48-hour experiment.
Yeah, okay. So you were doing these in the piston cylinder?
So we were doing these at 1 atmosphere, which was part of the reason we were having difficulty reaching textural equilibrium, because we would melt these sulfides and then just leave, void spaces behind as they would drain out of them, which, if we were doing it at pressure, or if it was occurring over a million years, that wouldn't be as much of an issue. So we've decided to kind of circumvent that by using just coherent chips of meteorites. And we're also trying some cold seal experiments to do this at between 1 to 5 kilobar pressures that are suitable for asteroid interiors.
Okay.
Yeah. I just sent some samples off to Zoltan Bachi over in University of Washington, St. Louis, to kind of follow up on those cold seal experiments. So yeah, it's been fun. Experimental stuff was something I dabbled with a little bit in my master's degree, and then, as you know, I did completely different things for my PhD. But it's good to be back into it now. It's fun stuff.
Oh, that sounds very exciting.
Yeah. So I saw Ureilites in the title, and I immediately thought of Liam. Is this some of the work that y'all have been working on? Okay, cool.
Yeah. Half of this is Liam's work now.
Okay,
Yeah,
cool.
or more than half. Yeah. Yeah.
Awesome.
It's a weird feeling describing work that someone else has really done the bulk of. I will try to do Liam justice.
All
I
right.
think he's hopefully going to show up today. So, in case anyone asks me difficult questions about Ureilites, I can just deflect to Liam.
I'm hopeful that Serena Goodrich will be able to make it. I mean, she is our resident Ureilite. Well, we're all Ureilite enthusiasts, but nobody more so than Serena. So.
Yeah. It's certainly you guys are a daunting audience.
We're friendly.
Yeah.
So I guess we'll start in 5-6 minutes or so at the turn of the hour. I usually give a minute or so for people to kind of trickle in. People often forget how to register and that kind of thing at the last minute, so give them a minute or so past the hour to log in, and then I'll just do a quick introduction and turn it over to you. So yeah, y'all did a technical test already for seeing how to share slides and everything, or have you?
Yeah.
Okay.
Yeah, it went fine yesterday.
Great.
Hi, well, I'm going to stop sharing my slide, and if you want to get yours going, Megan.
Sure, I can do that.
Great, thank you. And it's okay if we record it? I just want to make sure.
Yeah, that's fine by me.
Okay, great, thank you.
No worries. So hopefully you're seeing that okay.
Yeah, that's looking good on my end.
Great.
And I don't know if you've attended one of these before. Typically, the way that it's just structured is that we'll save the questions for the end. People can write questions in the chat throughout the talk, but we typically I'll just read them off at the end of the talk. So you don't have to. You can just ignore the chat box while you're talking. Yeah.
All right. Yeah. Oh, hi, Brian.
Hi, Megan.
Hey, how's it going?
I'm doing fairly well, I'd say. How about you?
Yeah, good, thanks. Yeah, it's good to see you.
Yep, just recently started down here at the LPI, so this is
Right, okay.
actually supposed to be in this seminar. So
Brilliant. And what are you working on these days?
I have bounced between so many jobs late in the past few years that I really don't have a straightforward answer to that. I am looking forward to getting into more meteoritic stuff and a few more proposals. I am currently also trying to finish writing a couple of papers on growing rare earth element crystals and feeding them to genetically engineered bacteria, which was my last postdoc.
Whoa.
Right. Yeah. It's you lose a job in the middle of a global pandemic, the likes of which hasn't been seen in a century. You take the postdocs you can find that involve a laboratory work.
But that sounds awesome. Was it awesome?
It was interesting. Let's go with that. I don't know how to. I haven't figured out how to build on it yet as part of a career. It would be nice to, but I have not yet figured that step out.
Okay. So who was it that employed you?
Esteban Gazelle and Megan Holycross at Cornell.
Oh, cool. Well, I keep referring back to your melts work on iron-rich planets, Brian.
Well, I'm trying to build on that right now and banging my head against 3 different software packages. Melts is actually the only one I have currently up and running. So that's
Oh, really?
Okay, yeah.
Yeah, I'm doing a project with Jessica Sunshine, actually, Sam's PhD advisor, and it's to do with spinel stability on the moon, which is, yeah, it's tough to model. Yeah. Yeah.
Is she still wanting to detect spinel-rich materials in asteroids remotely? Is that what Jess is after?
This is Sinus Astum is a very spinel-rich deposit that I think
Okay.
Jess was involved in the discovery of. I think she discovered this like very unique spot on the moon. Yeah, we don't know why it's there.
We will soon, right?
Hopefully, that's the idea.
Give folks another minute to trickle in, get their tea ready, get all prepped for questions.
Is this mostly internal LPI people, or is it attended by?
It's a mixture of I would say probably usually it's primarily LPI people. We typically have a good turnout from the broader online community, and we also have folks from JSC tuning in as well.
I kept attending these while I was at Cornell because it was the only way I could go to a planetary talk.
Yeah, well, now I know about it. Maybe I'll tune in.
Absolutely. We've got, I think, the weeks pretty much up through January, pretty solidly booked. So we've got a bunch of good talks coming up.
Great.
All right. I think we're starting to stable out in terms of audience numbers. So I'll go ahead and get us started. Just move some things around here. All right, well, welcome everybody to this week's LPI seminar. We are really excited this week to be joined by Professor Megan Newcomb. Megan is an assistant professor at the geology department at the University of Maryland. She leads the planetary volcanism lab at Maryland, where she and her students study the behavior of volatile elements in terrestrial and planetary igneous systems. And she's interested in controls on volcanic eruptive style, and the origin of Earth's water. Today, she's here to share her seminar talk, which is titled Efficient Degassing of Early Formed Planetesimals and the Ureilite Parent Body, Water Delivery to Earth via Unmelted Material. For those of you with questions, you can type those in the chat box and we'll address those at the end of the talk, or you can just wait till the end, virtually raise your hand, and I'll ask you to unmute yourself. So I'll turn it over to you now, Megan. Thanks so much for being here with us.
Thank you, Sam. Thank you for the invitation and the introduction. It's really exciting to be here and talk to you all about this work that we've been doing for the past few years to think about whether water can be retained during heating and differentiation of planetesimals and the implications that that might have for water delivery to the Earth. Okay. So I will just acknowledge my co-authors. In particular, I want to highlight Liam Peterson, my graduate student, who did a lot of this work, and also others at the Carnegie Institute for Science, where we're lucky to be able to use the SIMS, and Tony Eving and Adi Bischoff for providing samples. So the major motivation for this work and the talk I'm going to give today is thinking about where did Earth's water come from? And there are various objects that we can observe around our solar system that are potentially water rich and could explain how Earth obtained its water. So among those objects, we have the icy rich comets in the outer solar system. And in the very early days of solar system formation, there was a hydrogen-rich nebula cloud. And some people have proposed that Earth's water could have come, at least in part, from ingassing of that hydrogen-rich cloud into the growing planet. And then we also had a cacophony of planetesimals and planetary embryos floating around, each of which could have retained some water that could have delivered water to the Earth. So in just trying to decipher which of these sources or how much of each of these sources Earth's water came from, we can turn to the meteorite record. So meteorites are an incomplete sample of early solar system rocky bodies. And there are various different types of meteorites. So there are some called chondrites, which can be thought of as a kind of cosmic sediments. These are the very first things to precipitate out of the nebula, and they contain various components like chondrules, which are these kind of spherical features here you can see on the left, refractory inclusions, all set in a volatile rich matrix. And they have, by definition, they must have experienced some at least low level of thermal and aqueous alteration but they have not experienced melting. We know they experienced at least a low level of thermal and aqueous alteration, because without that, they wouldn't be cohesive enough to form a rock that could be flown through our atmosphere and land on the surface of the Earth for us to pick up and measure. But they have, at least some of them have only been very lightly heated or altered. And then we step up a heating grade to the primitive achondrites, which we think have experienced just low degrees of partial melting. And in many cases, their bulk compositions are similar to chondrites because they haven't fully differentiated. So they haven't segregated their sulfides and their metals into cores, and they haven't segregated crusts from mantles in some cases. And examples of these types of meteorites include the Ureilites, the Braconites, the Acapulcoites, the Lodronites, among others. And then finally, we have the achondrites, which have experienced extensive melting. They are from differentiated bodies that have undergone metal silicate segregation, and they likely come from bodies that had a magma ocean. So these include the HEDs, which we think come from Vesta, and the Angrites, the Orbrites, and the Martian meteorites, and also lunar meteorites. Something that has been like a huge shift in our understanding of the solar system that's come from meteorites research is this finding in 2011 that all of our known meteorites fall in two clusters when you analyze their Cap-17 oxygen and other refractory isotope ratios like epsilon 54 chromium. So this has been termed an isotopic dichotomy, where we notice the absence of meteorites in the middle here. On the left, in this kind of red field, we have what we call the non-carbonaceous meteorites, which include most of the achondrites and the primitive achondrites, like the Ureilites and the Angrites, also the Earth, Mars, and the Moon, and then some chondrite groups, the R-chondrites, the ordinary chondrites, and the enstatite chondrites fall in this non-carbonaceous group. And then on the right, we have the carbonaceous group. This includes mostly just carbonaceous chondrites, but there are a few weird achondrites among this group as well. And the thinking for how this isotopic dichotomy was set up is that we had to have spatial segregation among the different groups. And the general thinking is that the NC group represents inner solar system material, while the carbonaceous group represents outer solar system material. So one model for how this isotopic dichotomy could have come into being is that we had a change in the composition of infall from outside the nebula, such that early infall may have had the composition that is now typical of the CC reservoir. And then late infall was depleted in supernova-derived nuclides and became like typical of the inner solar system material. And that these two reservoirs were prevented from mixing either by the formation of Jupiter, which acted as a kind of barrier between the two reservoirs, or perhaps more recent models have suggested that the formation of planets in the early solar system forms at very significant condensation fronts, and that can also lead to this kind of segregation of these materials. So how does this all relate to the volatiles? One kind of natural consequence of these reservoirs being separated is that some of the materials are thought to have formed in the presence of ice beyond what we call the snow line, where water can precipitate into ice. And the NC reservoir is thought to have formed perhaps within the snow line, such that it it could have accreted more dry material. And so there are big implications here for this spatial segregation and its relation to volatiles. And simplistically, we might expect materials formed in the inner solar system to be less wet due to the presence, the lack of ice during their accretion, than materials that formed in the CC reservoir. Since Earth formed in the inner solar system, that raises the question of, how did we get our water? So if we did truly accrete in a kind of dry region, we have to explain, like perhaps our water, like we've clearly got oceans on the surface of the Earth. How did they get there? Well, one line of thinking is that we simply take some material from the outer solar system that accreted in the presence of ice, and then later on, we just deliver it to the inner solar system. And one model that's been put forth to explain how this might happen is called the Grand Tack. And in that model, Jupiter and Saturn are thought to migrate inwards and then outwards. And in that process, they scatter material from the outer carbonaceous reservoir into the inner solar system, where it can be tacked onto growing planets like the Earth. So a lot of work has been done to characterize the isotopic composition of various meteorite bodies, comets, and nebular hydrogen. And this isotopic work can help us to understand whether the Earth's water is consistent with delivery of carbonaceous chondrite-like material. And so on this plot, I'm showing there's nitrogen isotopes on the y-axis and the DH ratio on the x-axis. And you'll notice that the Earth, Moon, Mars, Vesta, and the Angrate parent body, they all cluster in this narrow region in isotope space at 0, 0 on this plot by definition. Okay, also on this plot, we have nebular hydrogen, which is very depleted in deuterium. And we have the comets, which are in general quite heavy. They're quite enriched in deuterium and quite enriched in 15 nitrogen. And then we have this group here, which are the carbonaceous chondrites, which actually extend to overlap entirely with the Earth. So we have very good agreement between the isotopic composition of Earth's water and the carbonaceous chondrites in general. So a simple solution to delivering Earth's water is just to deliver carbonaceous chondrite material to the Earth. It's also tempting to think on this plot, well, what if we kind of mix together cometry material and nebular hydrogen? Can we get something in the middle that looks like Earth's water? But if you calculate out mixing curves in this space, they are so strongly curved that actually they miss the Earth entirely. So it's not easy to explain the composition of Earth's water by mixtures of nebular hydrogen and cometry material. And from an isotopic point of view, the most simple explanation for Earth's water is that it came from a carbonaceous chondrite-like source. We can also mass balance, other volatile elements. And what we find is that the volatiles in the bulk Earth can be explained pretty well by addition of around 2 to 4% carbonaceous chondrite material to a volatile depleted proto-Earth. Now, this works really well for the majority of these elements. I'm sure you've noticed there's discrepancies with nitrogen and xenon. And I mean, there's a lot of uncertainties in these models. One argument put forth in this paper by Connell Alexander is that there may be difficulties in constraining the full nitrogen content of the bulk Earth, and xenon is thought to have maybe been lost to the atmosphere. But in general, we have a good match for the majority of these elements. And there's other evidence from the angrates that carbonaceous chondrite material was added and can explain the angrate's volatile budget. So here we're looking at chondrite normalized concentrations of elements against their condensation temperature, which is effectively a proxy for volatility. And so on the left, we have refractory elements, things that are not volatile. And on the right, we have our highly volatile elements like hydrogen, carbon, and nitrogen. And in this curve here, the dashed curve shows what a volatility trend would be expected to look like if you took a planetesimal or a planet and you heated it up and you boiled off the volatiles. So the highly volatile elements should be very strongly depleted, but what's observed for the angrites is that they plateau out like this. And so the concentrations of hydrogen and carbon are actually pretty similar to the concentrations of much less volatile elements like rubidium. And this trend, or this flattening of the most volatile elements in the angrite parent body, is most easily explained by simply adding some carbonaceous chondrite to a volatile depleted parent body. So the green curve here indicates addition of 0.3% carbonaceous chondrite material to a volatile depleted angrite parent body. So with the isotopes and the mass balance on the Earth and the angrites, it seems like we have a pretty strong case that water in the inner solar system could simply have been delivered by carbonaceous chondrite material after the main phase of accretion. And so you might think, well, can I pack up now? We don't have to listen to the rest of this talk. But there are some complications that I would like to explore. So late delivery models, they make this assumption that the terrestrial planets accreted dry. And that might not be the case, right? So we have families of chondrites that we know accreted in the inner solar system, things like the ordinary chondrites and the enstatite chondrites and the R chondrites, and they all contain volatiles. Not as much volatiles as the carbonaceous chondrites, but potentially enough to explain the terrestrial volatile budget. So yeah, perhaps the inner solar system is not bone dry. Perhaps there's water bearing material available. And so then we need to ask the question of, okay, if there's volatiles available to be accreted to the inner solar system planets, are those volatiles going to be retained during accretion, or are they going to be lost during early melting and metamorphism? So that's the main question I want to address today. There's some evidence in the literature that perhaps Earth's water didn't come from carbonaceous chondrites, but may be explained by accretion of enstatite chondrite meteorites. And the attraction of this is that in terms of all of its other isotopes, the enstatite chondrites are a really great match to the Earth's isotopic composition. So if we could explain Earth's water from enstatite chondrites, that also seems like a fairly nice, viable mechanism. So these authors, Piani et al. In 2020, published this paper where they found that the enstatite chondrites really have quite considerable water contents. And of particular notes, the aubrites plotted here, these are the differentiated equivalents of the enstatite chondrites. They also seem to have relatively high water contents. And this might suggest that the water that the enstatite chondrites had was not lost during differentiation and melting. And so if that's the case, it opens up the question of, like, did Earth obtain water during its primary accretion phase? Do we really need this delivery of wet carbonaceous chondrite material? And other recent work has argued that primitive achondrites like the Ureilites could be an important source of Earth's volatiles as well. And so this is a study by Mark Hirschman from 2016, and he finds that the general shape of Earth's volatile element trends in hydrogen, nitrogen, carbon, and sulfur, they're pretty well matched by a late veneer composition that has 80% Ureilite material and 20% carbonaceous chondrite material. So given that we've got growing evidence that there's water in the inner solar system and that certain achondrites may be retaining their water or their other volatiles, we need to explore the effects of water loss during melting and thermal metamorphism to really kind of rule out or accept this possibility that Earth accreted water from the inner solar system during its primary accretion window. So the question is, does the presence of water in achondrites like the angrite parent body and the Earth, does that require late delivery of carbonaceous chondrite material, or can we simply just accrete the volatiles during the primary accretion? To answer this, we're going to look today at data from two sets of meteorites. So one set is these very rare achondrites that accreted in the water-rich carbonaceous chondrite region. So we know that these accreted beyond the snow line, and they should have accreted a ton of ice, but they may or may not have retained the water that they accreted as they melted and differentiated. And then the second group of meteorites that we're going to look at are a suite of primitive achondrites called Ureilites, and these only partially melted, and they never had a global magma ocean. And so we can use the Ureilites to answer the question of, is a magma ocean required to outgas volatiles? So we want to gradually piece together, from materials we know we accreted water, and also from materials that we know only partially melted. At what point is water lost? How efficient is water loss from these materials during accretion? Okay, so I'm going to begin with that first suite of samples. There are rare achondrites that have been found with isotope signatures that are typical of carbonaceous chondrites. And I'm showing them in blue here on this plot. So this is the same plot that we saw before. It's Cap17 oxygen against epsilon 54 chromium. And among the carbonaceous chondrites, we have a few samples that are melted and differentiated. And so we're going to analyze a group of achondrites that came from this carbonaceous chondrite group and compare them to some other ungrouped achondrites from the non-carbonaceous group, and basically see if their water contents differ. So we've analyzed volatiles in this selection of ungrouped achondrites here. On the left, I've got a panel of the carbonaceous affinity achondrites. So we have Northwest Africa 6704 and 10132, which are paired. They're thought to have come from the same parent body. And then Northwest Africa 2788 and 6962. So we have a total of 3 parent bodies represented on the left. And then on the right, we have 8409, 8777, and 11558. So just looking at these pictures, you can get a sense of the petrography of these things, and most of them appear to be fairly primitive compositions. They are rich in orthopyroxene, or they're rich in olivine. And because they're so rare, and a lot of these were discovered quite recently, and there's not a huge wealth of knowledge about these samples. But Northwest Africa 6704, we do have more of a geochemical context for that sample. And so this Hubaya study from 2019 has published whole rock data. And what they found is that Northwest Africa 6704 is approximately chondritic in all but the most volatile elements. And this suggests that, the interpretation given in that paper is that the parent body is perhaps flash melted and then rapidly recrystallized, such that only the very highly volatile elements appear to have been lost. The exceptions to these being primitive are these. On the right, we have a couple of crustal lithologies represented. So Northwest Africa 8409 is a gabbro, and 11558 is an andesite. So you'll notice that among these samples, we have fairly small quantities, and we've got basically solid rocks and lots of crystals, but not much glass. And so in order to characterize the volatiles, we're going to be measuring predominantly volatiles in the nominally anhydrous minerals. And so I want to talk a little bit about how we go about this and how water measured in these nominally anhydrous minerals might relate to water in a coexisting magma, and also to the parent body more generally. So what we typically do when we quantify water in these nominally anhydrous minerals, we can relate the water that we measure to the water that would be in an equilibrium melt composition by using a Henrian partition coefficient, which is often called KD. And so, for example, for olivine, the partition coefficient is the ratio of the water measured in the olivine to the water in the equilibrium melt. And typical values of this partition coefficient that have been found in terrestrial compositions range from around 0.0007 to 0.002. So they are very, very small, which means that barely any water partitions into olivine. It's strongly incompatible in olivine. And the water that is in the olivine, I'm calling it water, but it's really protons, and those protons are charge balancing defects in the crystal. And so if we take a kind of average partition coefficient of 0.001, what that means is that an olivine containing around 10 parts per million water would be in equilibrium with a magma that contains 1 weight% water, or 10,000 ppm. And so if I give you a value of water measured in olivine, what you can do is multiply it by 1,000 to find what the water in the coexisting magma would be. Similarly, if we look at water in clinopyroxene, for example, the partition coefficient for water in clinopyroxene is a little higher. It's around 0.01. And so a clinopyroxene that contains 100 parts per million water would be in equilibrium with a magma that contains 1 weight% water, or 10,000 ppm. So for clinopyroxene, what we do is we take the measured water in the clinopyroxene and multiply by around 100 to find the water concentration of the coexisting magma in ppm. Okay, so to give me a break and to help you guys calibrate, I've put in a quiz. This is something I've learned from teaching the past few years. If anyone's feeling brave, you can put answers in the chat. Otherwise, I'll tell you the answers in about 10 seconds. Okay, so let's start with question 1. If you have a mid-ocean ridge basalt, MORB, that contains around 2,000 parts per million water. And so a crystal of olivine that forms in mid-ocean ridge basalt, you would have to take this 2,000 and divide it by 1,000 to work out the expected equilibrium concentration of water in that olivine. So water in a morb olivine, you'd expect around 2 ppm. So tiny, tiny quantity of water. And in a CPX, we'd instead divide by 100. So you'd expect around 20 ppm of water in a morb CPX. And then question 2 is about CI chondrites, which are among the wettest materials in the solar system. So CI chondrites contain around 14 weight% water, or 140,000 parts per million. And so if you took a carbonaceous chondrite material and flash melted it somehow and crystallized out olivine from that melt, then you would take this 140,000 ppm and divide that by 1,000 to get around 140 ppm in the coexisting olivine. And for clinopyroxene, you'd divide by 100, so you'd expect maybe around 1,400 parts per million in a coexisting clinopyroxene. So hopefully this calibrates our intuition a little bit about the kind of expected water concentrations that we might find in these nominally anhydrous minerals in igneous systems. That is where the minerals are in equilibrium with a coexisting melt. Okay, so they're very small quantities, and this makes the measurements quite difficult. And we're lucky to be able to use the nanosims and the 6F sims at the Carnegie Institute for Science, where we measure water, carbon dioxide, fluorine, chlorine, and sulfur in these nominally anhydrous minerals. So I'm showing on the left the picture of the lab, and on the right, I'm showing a calibration curve. So what we do is we take samples of known water concentration and we measure their OH to silicon ratios using the SIMS, which are multiplied by a factor to correct for the varying silica contents of the minerals that we're looking at. And we plot those ratios against their known water concentrations. And thankfully, there's a study by Kumamoto in 2017, and they did our community an amazing service of measuring, and they measured standards, they characterized standards, which they then sent to the Smithsonian so that anyone can check out these standards. And there's a collection there of orthopyroxenes and clinopyroxenes that can be used to calibrate nominally anhydrous minerals. And you'll notice that the water range of the standards here is from 0 up to just over 200 parts per million. So one of the most difficult parts of the work that we've been doing is the fact that our water contents are so low. And so we really need to know our analytical blank very, very well. And we've been trying to assess the blank using, we measure materials that basically have no water in at all. And what's typically used in labs across the world are suprasil glass, which is a glass manufactured by a company called Ureilite that is known to have very low water contents. And also we can use synthetic forsterite. This would be forsterite that has been made at low pressure and high temperature in a furnace, so it has basically 0 water. So what we've been doing in our group is measuring both of these materials in multiple sessions. And we have found that over several sessions now, that suprasil glass always has about 2 ppm more water than synthetic forsterite. And this is really useful to know, partly because suprasil is a widely used blank material, but also because when we measure this 2 ppm offset, it helps us to know that we can detect such small differences in water content. So it's a really nice kind of quality control when we see this 2 ppm offset. We're actually compiling these measurements of supercil and synthetic forsterite in an open source GitHub repository, which is called SimsBlank. So if you are ever using supercil to quantify your blanks, you can come here to find our most recent kind of global value across many, many sessions that we've been measuring. And so I want to just very quickly run over some of the other challenges that we faced when making these measurements, because they're really quite tricky measurements. So for the sample prep challenges, we have to avoid using epoxy at all costs because epoxy outgasses in the sims and it ruins our background. So instead we use very soluble dental resin materials that can be dissolved cleanly. And we clean our samples after polishing with multiple cycles of acetone, toluene, and isopropanol. We bake them in a vacuum oven, and then we press the crystals or the little chips into indium metal, which is organic free. We have to ensure that the sample surface is completely conductive, so we coat it in gold, and we also have to make sure that the indium laps up right to the edge of our grains, so there aren't any gaps or any relief on the sample surface. And then we have to put our standards in the same sample folder as the unknowns to avoid any kind of sample change, which would break the vacuum in the chamber and might change the conditions. During the analyses, we can do other things to try and minimize our background. So if we're able to, we will put the samples in our mass spec weeks before the analysis so that they can pump down under the turbo pump and get a really good vacuum. We use matrix match standards whenever possible. We try to use high primary beam currents, although we obviously are sharing this facility with multiple other people and they don't always like us cranking up the beam current really high. We aim to get a really stable beam and electron gun, and we use things like electronic gating that enable us to just select the ions from the center of our craters to avoid high contamination. We use a function called real-time imaging, which enables us to see the ions coming off the surface in real time. And if we are on a crack or something in the sample surface, that will show up as a giant hotspot in our analyses. The carbon counts will be really, really high. The hydrogen counts will be really high. And we'll be able to see features like that, like cracks or other contamination. And we can move the beam away from the contamination and check that our analytical area is really clean. We measure carbon not because we think we're going to detect carbon in these phases, because carbon's extraordinarily incompatible, but we use it to screen for organics contamination. So sometimes we'll get carbon counts that are, a factor of 10,000 higher than all of our other analyses. And that will tell us that we accidentally hit something that we shouldn't have hit. And then we monitor our blank by measuring dry materials very, very frequently. And we use those analyses to calculate our limits of detection and limits of quantification to make sure that we're able to quantify the water concentrations that we're measuring. And then we use secondary standards to monitor drift caused by things like variations in the primary beam current. So for the sessions that I'm showing for these ungrouped achondrite minerals, the blanks that we achieved were around, it was 0.6 ppm once we blank corrected. So we measured just over 1 ppm water in our synthetic forsterite blank, which we think has 0 parts per million water. And we measured about 3.5 ppm in supercil. And if I add our data to this, what we find then is that our carbonaceous and non-carbonaceous achondrites contain less water than supercil glass, so much less than 2 ppm water. And this is across multiple phases and many, all of our meteorites with no exceptions. And so these samples are extraordinarily dry. If we blank correct our data by subtracting out the values that we measured in synthetic forsterite, then that allows us to place a very conservative upper bound of 2 parts per million water in our meteorite anomaly anhydrous minerals. This is based on a session in which our detection limit was 2 ppm, but effectively the vast majority of our analyses are below detection. So what I'm going to be reporting here is upper bounds on their water content. So these measurements, there's measurement of less than 2 parts per million water in an orthopyroxene. This is among the driest measurements of extraterrestrial or terrestrial materials that have been reported. So there's this nice compilation by Pellier et al. In 2010, and you can see that most orthopyroxenes contain tens up to a few hundreds of parts per million water, and ours are really at the extraordinarily low water end. An equilibrium melt in equilibrium with an orthopyroxene containing 2 ppm would contain less than 100 parts per million water. Our analyses show that these ungrouped achondrites have minerals that are drier than similar analyses that have been made on the moon and in other achondrites. So these are our analyses here of the CC achondrites and the NC achondrites. They've been grouped into parent bodies. So we have 3 parent bodies represented for the carbonaceous chondrite affinity achondrites, and 2 parent bodies represented for the non-carbonaceous achondrite parent bodies. And then you can see that they're lower than analyses that have been made of anomaly anhydrous minerals in angrates, in eucrites, and even these anorthosites from the moon. As a comparison to the existing angrates data, here's a profile that was measured by Adam Sarafi and others in 2017. You can see that the water contents are ranging from around 20 ppm to about 6 or 7 ppm in this olivine. And if we plot on our olivine analyses, they're considerably lower. So we can apply Henrian partition coefficients to our analyses to get upper bounds on the water concentrations in the coexisting silicate melts that these minerals may have crystallized from. And a lot of these are pretty conservative, right? Because water is so incompatible in olivine and orthopyroxene. And what we're reporting is an upper bound on the water contents of those minerals. So their true concentrations may be a lot lower. We would consider this sample here to be one of our best constrained samples because we were able to find melt inclusions in Northwest Africa 6962. And in the melt inclusions, we measured an upper bound of 38 parts per million water. So if we consider that parent body further, there's some evidence that Northwest Africa 6962 may have formed by crystallization of a 30% melt of chondritic precursor material. And so if we apply an equilibrium melting model to this parent body, then up to 38 parts per million of water in the melt results in a parent body that contains around 13 parts per million water. And so effectively what our data are suggesting is that all of these parent bodies of these ungrouped achondrite meteorites were extraordinarily dry, and this is regardless of their formation either in the inner or the outer solar system. So a corollary of this result is that just having a carbonaceous chondrite signature does not necessarily indicate water-rich material. So some models out there are using a CC signature in terms of like refractory isotopic composition to indicate the fraction of water-rich or volatile-rich material that could have accreted to inner solar system bodies. But I would say, well, some of these things should be read, right? Because they're not necessarily water-rich. Anything that melted in the CC reservoir would have been dry. Okay, So we can now address this first question. We've got these rare achondrites that accreted in the water-rich carbonaceous chondrite region. We know they accreted water. We now know they did not retain their volatiles during melting and differentiation because all of the 3 parent bodies that we analyzed are bone dry. So now I'm going to move on to question 2. We're going to look at some Ureilites data. So the Ureilites are primitive achondrites that only partially melted. We know they never had a global magma ocean. So now we can ask, is a magma ocean required to outgas volatiles? So this work is led by my graduate student, Liam Peterson, and we'd like to acknowledge that Liam won this NASA Future Investigators Award that's supporting this research. And I'll admit that I was a little nervous coming to talk to you guys today about the Ureilites because I know how much expertise there is in this room, particularly Serena Goodrich has been, she's widely acknowledged as the Ureilites expert. So I thought before this talk, I better go and try and review some of all of Serena's work. Let's see if I can. I didn't have a hope, but I thought I'd speed read some papers just in case. And what I found was when I opened this paper by Serena in 2014, in the introduction, this direct quote from Mike Drake, who said, "Nobody has ever figured out Ureilites, not even me." So I can't say I benefited too much from my speed reading, except to feel better because the Ureilites are famously complex and very, very difficult meteorites to understand. So I appreciated that. So why are they so complicated and weird? Well, they're very carbon rich. They are mostly composed of olivine and pigeonitic pyroxene that's set into a graphite matrix. And we think they're very early formed, and we don't think that they had a global magma ocean. So what's the evidence for that? Well, they exhibit a very wide range of Cap-17 oxygen. Now, Cap-17 oxygen is supposed to have a nebular origin. And so you'll notice that most of the nice achondrite parent bodies on this figure, like the braconites, the renoniites, the acapulcorites and lodronites, they have a very limited range of Cap-17 oxygen, indicating that whatever they formed from the original nebula, it's been homogenized. The Ureilites occupy this whole region here. They have a huge range in Cap-17 oxygen. And so that indicates that they accreted from quite distinct nebular materials, and they didn't have a global magma ocean that would have homogenized that material. So we think that they capture a very early stage of differentiation on an early formed parent body. So they probably accreted within 1 million years of solar system formation and disrupted by around 5 million years. Intriguingly, they have a similar carbon-nitrogen ratio to the Earth. And so they've recently been cited as a potential source of terrestrial volatiles because of this. But note on this plot the lack of hydrogen data. So until Liam's work, we didn't really have good constraints on the hydrogen content of the Ureilites. So Liam has addressed this big gap in the literature by analyzing volatiles in both the main group Ureilites and also in a crustal lithology Ureilite called ALMA. And so the main group Ureilites are thought to represent the mantle of the Ureilite parent body, and ALMA is thought to represent the crust. So among the mantle Ureilites, these main group Ureilites, Liam found that the olivines contain less than 10 parts per million water, and the chynopyroxenes contain less than 6 parts per million water. And then in ALMA, the crustal lithology, Liam's measured a number of melt inclusions in the pyroxenes from this meteorite, And he found this very intriguing trend where the melt inclusions have variable water that relates to their diameter. And so we have an increase in water content with decreasing diameter. And this kind of trend could be produced by post-entrapment crystallization of pyroxene on the walls of the inclusions. And so based on this, we actually think that the largest melt inclusions represent the best constraint on the initial liquid composition, in part because they would be less volumetrically affected by post-entrapment crystallization, and also because of the agreement of those values with measurements of interstitial glass. So we actually think probably the best water content to represent the liquid that was produced by melting the Ureilite parent body is around 50 parts per million. So we have analyses of both the liquid that was produced by partially melting the Ureilite parent body, and also what represents the residue of melting the Ureilite parent body. And so we can use both of these analyses to try to constrain what the bulk Ureilite parent body would have contained. Liam applied 3 different approaches. The simplest and first one is just mass balance. So you take the restite or the main group Ureilites and the melt, and you apply a known melt fraction of around 15% and simply mass balance the amount of restite and melt. The second approach is a batch melting model. This is oversimplified for the Ureilites. We don't think that the Ureilites underwent batch melting, but it's a nice first step that's quite easily comparable to calculations that have been done for other parent bodies. And you can do it multiple ways. You can start with the liquid and constrain using the batch melting equation, the concentration of water in the solid and the bulk, or you can start with the solid and constrain the composition of the bulk that way. And then the last method that Liam applied was this continuous or dynamic melting model. And so Liam's used the model proposed by Shaw 2000 and a mineralogy or lithology proposed by Barat et al. 2016. And so continuous melting, for those who aren't familiar, says that you melt in increments. So I'm showing on the right here what continuous melting might look like. We've got different increments of melting the residue, and those are tapped one by one and put into this supposed crustal magma chamber, perhaps at the top. And importantly, you leave behind a residue of melt. So some melt stays behind in the mantle. And so this allows a better match to trace element data from the Ureilites, which is why it's been proposed as a good model for that parent body. So by applying these 3 different methods, these are the values of water content that we find for the Ureilite parent body. We consider the most robust constraints to come from the mass balance, which is quite nice and simple and isn't melting model dependent. And also this aggregate melt variety of the continuous or dynamic melting model. And those preferred values or those models give us a range of bulk Ureilite parent body water contents of around 3 to 20 ppm for the bulk parent body. If we assume that the precursor material for the Ureilites was similar to CI chondrites, which has been argued, then Liam's results suggest the main group Ureilites lost more than 99.9% of their accretionary water. So again, water loss was extremely efficient, and the Ureilite parent body is on average more depleted than Vesta and the Angrite parent body. Even if we modify the precursor material and assume it started as an ordinary chondrite or just organics, in each case, we calculate a % water loss for the Ureilites of much more than 99%. So we have extremely efficient water loss. And something else that's interesting about this is that the Ureilites are so reducing that their carbon is refractory graphite. So while sometimes we might think of volatiles kind of moving together, I think it's important to consider that under really reducing conditions, the speciation of volatiles changes and you can have extreme decoupling between the different volatile elements. So even though the hydrogen was very efficiently stripped out, the carbon was still retained. Okay, so these results from the Ureilites suggest that you only need to partially melt to strip out your volatiles. You do not need a global magma ocean to outgas volatiles. And so both lines of evidence are pointing to very efficient water loss during melting and thermal metamorphism on planetesimals. So why would primitive achondrites be so dry? Well, there's many reasons. You have heating from within by 26 aluminum decay. We have flash melting by impacts that can cause degassing of volatiles into space. And you have outgassing of more global magma oceans. And really only the largest planetary embryos would be capable of retaining an atmosphere. And so the last calculation I want to show you guys today is how large a planetary embryo would need to be to retain hydrogen. And we considered two different situations. One is relatively low temperature thermal metamorphism. And at 500 degrees C, it's thought that the speciation of hydrogen would be methane in the ordinary chondrites and the enstatite chondrites, or water from carbonaceous chondrites. And you need your planetesimal planetary embryo to reach around 1,000 kilometers radius in order to retain the water and the methane. If we increase the temperature to conditions that are more typical for magma ocean degassing, then we can calculate that you would need around a 3,000 kilometer radius to retain molecular hydrogen and around 1,000 kilometer radius to retain water. And so this would be, hydrogen would be outgassed under more reducing conditions, such as for the Ureilites. So if we couple our results with thermal models of planetesimal formation, what we find is that in order for a planetesimal to retain its water, you have a couple of options. One is that you can accrete early, but remain very small, like less than around 30 kilometers. And the other option is that you can accrete late, after around 2 to 4 million years, when the 26 aluminum has already decayed. I don't have time to go into that today, but I refer you to this really cool study by Lichtenberg et al. 2019 for a more detailed look at that calculation. So to summarize, we analyze volatiles in carbonaceous and non-carbonaceous achondrites and Ureilites, which are primitive achondrites. These samples represent the very earliest stages of planetary accretion and melting. And they're really dry. It's quite a simple conclusion. So we think that degassing of planetary embryos or planetesimals during 26 aluminum heating or impact events is very efficient. And our data from the Ureilites demonstrate that a global magma ocean is not required to lose water. So we think water was likely delivered to Earth via unmelted material. And one of the significant things about this result is that if you find a carbonaceous chondrite signature in a meteorite, that doesn't necessarily indicate water-rich material. So with that, thank you very much for your attention, and I'd be very happy to take any questions.
All right, thanks so much, Megan. Audience, feel free to express your appreciation through your virtual clapping. And for those of you with questions, you can raise your virtual hand. I'll call on you to unmute yourself, or you can alternatively type that in the chat box. So don't be shy and ask your questions now. Okay, we got one from Micah Shawel. Go ahead, Michael.
Great. Yeah, my name is Mike. I'm a research scientist at Georgia Institute of Technology. Really cool talk. I very much enjoyed it. I was actually thinking while you were talking about some of the ideas that you got into there in the last few slides, which were what would the implications for this work be for the moon, actually, and in particular, how much would we expect the sort of lunar mantle materials to have undergone outgassing, and would this suggest sort of the idea that in fact, as we found in a lot of lunar samples, there is some, there probably was some significant fraction of water in the original lunar mantle. And so I was wondering if you had any thoughts about that.
Yeah, what an interesting question. So let's see. The moon forming impactor was thought to be like probably Mars sized, which is about the size that you would need to be able to retain things like hydrogen and water. I think, I mean, the moon water during the impact and the generation of that accretionary disk that then reaccreted to form the moon, I know that we all initially thought, well, surely all of the water would have been boiled off. And then people from Dave Stevenson's group, like Miki Nakajima, have done modeling work to show that perhaps hydrogen loss is diffusion limited during that process. And that could be how you would retain it in the lunar interior. And that's probably, I think that's the extent of my knowledge on that, but certainly it outlines that these seemingly high temperature accretion processes don't always necessarily result in like complete volatile stripping.
That's great. Thanks so much, Megan.
No worries.
All right, we got a question from Tim Lichtenberger. Go ahead and unmute yourself, Tim.
Hi there. Hi, Megan. Nice to meet you.
Hi.
Great talk. Thank you so much. I have two questions. One is related. So you basically motivated in the beginning your study with the usually expected temperature gradient in the disk. But you seem to be very open about the inner solar system is actually quite full of volatiles. So my question essentially was to the experiments. Do you have what's your view on where the volatiles, if they were volatiles in the first place, where they come from? What is the physical mechanism for this? Yeah, maybe I'll leave it there first and then come to the second one.
I'm so glad I didn't try and explain your figure in front of you. I didn't realize you were here. Right, so in terms of volatiles in the inner solar system, I think that there's evidence that the snow line has moved around, right? And that the snow line might have been quite a lot further in than its present day condition. So certainly that could help with accreting water. But the experimental or measurement evidence mostly comes from Conal Alexander's work, he's been measuring, ordinary and endocyte chondrites for a long time and really showing that they contain appreciable water. Now they may have accreted a little later than the most of the achondrites, but it's definitely it's pretty definitive evidence that there was some water in the inner solar system, I think. Yeah, did you want to add to that?
Yeah, it brings me to the second one. Essentially, you had this one slide where you said that H and C decoupled by from degassing, right? Saying something about the red oxygen fugacity or the redox state at that state, suggesting, if I understood you correctly, that it should be relatively low in redox state if the C is in graphite.
Yeah.
Does it tell us something about the reprocessing by the heating, or does it tell us about the phase the H and the C were accreted in the first place?
Yeah, so the carbon exists as graphite because it's a very reducing body, and because it exists as graphite is refractory. So carbon has a choice. It can, if it's maybe carbon monoxide or carbon dioxide, then it's very volatile. But if it's formed under reducing conditions and it exists as graphite, then it becomes refractory. And so that is why the water would decouple from it, because the water, as the water becomes more reduced, it becomes molecular hydrogen or maybe methane. And that is still extremely volatile. And so that's the difference. You've changed the FO2 condition and it has a different effect on the carbon volatility to the hydrogen volatility.
Thanks.
No worries.
I've been told that the chat was disabled. So for those of you who were trying to type, you should now be able to type. So thanks for whoever that was that named themselves chat is disabled. Very clever. I have a quick question, I guess, while that's being asked. So the KD values that you got for, or that you were using, I think from experimental work, looking at olivine and melt and pyroxene and melt KDs, how much does melt composition affect that at all? I mean, like we're applying this for a range of materials. So like, could you just, I guess, comment on that?
Yeah, so the partition coefficients will be affected potentially by things like oxygen fugacity and water content potentially, which is related to a pressure dependence. So particularly for water speciation in melts varies as a function of like pressure and water content. So at high pressures and high water contents, you expect to see more molecular water, and at low concentrations of water, more of the water is as hydroxyl. And that certainly we expect to affect the partitioning. I think that current partitioning data and studies haven't quite managed to tease out those kinds of effects, but there are some strong effects in certain phases with FO2. So like when you get really reducing, water suddenly becomes more compatible in feldspar, for example. So we do have to try and use the appropriate partition coefficient for our system. And something that Liam is currently working on is teasing out that pressure dependence for the partition coefficient of water in olivine.
Cool. Quick follow-up, I guess, to that then. So for the samples you had that had the melt inclusions within them, when you took, the SIMS measurements of the water content for the individual anhydrous minerals and the melt inclusions, and I missed whether or not you had any bulk measurements on that. Do those all still fit on those calibration curves that you were mentioning at the beginning?
Oh, so we have a different calibration curve for the melt inclusion analyses. We use a suite of basaltic or rhyolitic glasses for those, depending on what their compositions are.
Cool.
Yeah.
All right, thanks.
No worries, thank you.
Do we have any more questions from the audience now? Our newly enabled chat feature? Or otherwise? If not, then I'm marking about 8 or so minutes past the hour. So if you do have questions, I'm sure Megan would be happy to correspond with you and answer those. Otherwise, thank you so much for being here with us this week, Megan, and for sharing your talk with us. It was really interesting. And audience, if you'd like to express your appreciation one more time, you can do so in the chat box or however you choose to do that.
Thanks very much, Sam.
Yeah, thank you, Megan. And thanks everybody for being here. We'll have another next week. I believe it's Zoltan Vaci. So we'll have some more experimental work to hear about. So we'll see you all next week. Thanks so much.
Thank you. Bye.
See you, Megan.